Okay, so what is this equilibrium constant? The equilibrium constant is a way of quantifying the relative concentrations of reactants and products that we see at equilibrium. And so here's our generic equation that we use a lot. So we've got two reactants, A and B. My pointer's not behaving. Two products, C and D, and they have coefficients. We've got the double-headed arrow here. The reaction can go both ways. When we have the symbol or the formula for an element, a molecule, with brackets around it, just to refresh our memory, that means the molar concentration of that. So the concentration in moles per liter. And here's a note. So K is the abbreviation for Kelvin, and this italicized K is the equilibrium constant. See how different those are?
So wait, it is a capital K?
Kelvin is a capital K.
No,
Equilibrium constant is a capital K.
Wasn't it a lowercase K?
That was the rate constant.
Oh.
The rate constant, yeah. Rate constant is lowercase k. Kelvin is capital K, and equilibrium constant is capital K italicized. Yeah. Okay, so just be aware of that. The good news is that equilibrium constant and the abbreviation for Kelvin are rarely on the same page, right? They're just not together very much. Okay, so the equilibrium constant is defined this way. The molar concentration of product C raised to the power of the exponent in the balanced chemical equation times the molar concentration of D raised to the power of its coefficient. So the products on top and the reactants on bottom. Again, the concentration of A to the A power, concentration of B to the B power. And this is commonly known as the law of mass action. Don't ask me why, because I don't know. But there it is, it's the law of mass action. But this is the definition of the equilibrium constant. And if this looks vaguely familiar, it's because we do teach this in Chem 3A. So you may remember it from that. Okay, so according to the law of mass action, what's the correct expression for the equilibrium constant for this reaction? We have 2A plus B going to 3C. D, I'm getting some votes for here. So we want the product, C, raised to the third power, divided by A to the second power and B to the first power. And so, yes, D is the answer. Okay? So when we apply the law of mass action to a balanced chemical equation, we come up with things like this. So for this chemical reaction, we can define the equilibrium constant as the NO2 concentration to the fourth power times the oxygen concentration divided by the N2O5 concentration squared. The coefficients from the balanced chemical equation become the exponents in the equilibrium expression. Yep.
This might be a dumb question, but mathematically, I'd like to know why that works, changing the coefficient to an exponent.
I would too.
Oh, okay.
Yeah, so mathematically, why does this work? It seems too convenient that this would end up being a constant. I mean, you can't just decide that, oh, we're going to do it this way, and it's always a constant, because we can change these concentrations, and this is still a constant. And so it is almost magical, if you ask me. Mathemagical. Yeah.
Oh my gosh.
This is what happened when you have classes at night. Yeah. But what?
Because 4 times a number is not the same as that number to the fourth power.
No, it isn't. It's not. Not at all.
Proofs of this on YouTube or something?
Honestly, I'm not sure how you'd go about doing a proof of this, but we'll see data where it's going to work. Yeah.
I'm gonna ask my
But that's a great question. And I have that question too, but you know, when I leave class, I'm going to get busy with something else and I'm going to forget to look into it. You know, that's how it works. So express the equilibrium constant for the combustion of propane as shown by this balanced chemical equation.
Do you have any suggestions on how we, like, does it really matter, but like how we can really separate a K from an italicized K when we're writing it?
Context? Yeah.
I think they make it pretty obvious.
No, like when you're writing it.
When you're writing it,
You're writing,
yeah.
Just make
It really comes down to context. You know, when you're reading handwriting or reading your own handwriting, you know, if you just looked at an individual letter, would you be able to tell what it was? Maybe not, but with the rest of the letters around it, you can see that it's an S and not a 5. Right? That's what makes reading your data so difficult, is it's numbers and there's no context. Okay, so let's do this. You've had a little time to think about it. So K, and honestly, can you distinguish between an italicized K and a non-italicized K in handwriting?
Yeah. There's a plain
Possibly, but mine always bend a little. So, but I do try, and it's very tedious, but I do try to do that consistently in the PowerPoint slides. And the book does that as well. Okay, so what are we looking for in the numerator here? The products. So the first product we see is CO2, and the coefficient is 3, so that's the exponent. And the next one is H2O, and its coefficient is 4, so that's the exponent. The reactants go in the bottom. So we've got C3H8, and what's the exponent for that one? 1. It's an unwritten 1 here, and so we can leave it an unwritten 1 there. And then we have O2 to the 5th power. That's it. Isn't it nice? It's just this pattern and you do it. Yeah, I like this math. Well, we'll learn more about it, but this is basically it. Yeah. I remember having a hard time remembering, did I put the products on top or the reactants on top? And so it is a little bit like delta, where it's final minus initial. It's the final over the initial. So it's the products over the reactants, always. Yeah.
If you were doing this for the reverse reaction, would it be upside down?
We'll talk about that. Okay, so the significance of the equilibrium constant. So if K is large, and by that we mean much, much bigger than 1, that means that the numerator of that expression is much bigger than the denominator, right? And that indicates that the product concentrations are much higher than the reactant concentrations. So this is an example of a large equilibrium constant. 1.9 times 10 to the 19. That's a big number, right? So if that's the equilibrium constant here, then the HBr concentration must be much bigger than the H2 and the Br2 concentration at equilibrium. Yes?
What dictates that? I mean, like, what circumstances would...
Cause the equilibrium constant to be large?
Yeah.
Chapter 19. That comes in chapter 19. Just wait on it. Yes?
We had talked about a large K means that the reaction favors the products.
Mm-hmm.
Does that mean it's more so a forward reaction?
Yeah.
And
It'll go more forward. And then here's the small k, and here's an example of a small equilibrium constant, 4.1 times 10 to the minus 31, right? Super, super small. When we've got a very small number for our K, that means that the reactant concentrations are much larger than the product concentrations.
I think my brain is working too much right now, but is this why, like, in certain things are just not standard? Or is this measuring?
Well,
their
this is
instability?
this is measuring how far a reaction goes. This process, this also applies to things like solubility. So, we learned in Chem 1A that silver chloride is insoluble. Well, does that mean that no silver ions dissolve? No. It means that very few. So if you do an equilibrium constant for the solubility of something and the number is very, very small, that means that the number of dissolved particles is extremely small compared to what you started out with.
Right, but I mean, like, even nitrogen monoxide in nature, like, it doesn't, like, you will find more nitrogen and oxygen versus
Yes.
that in a sample even.
Right. So if you were looking at a sample of gases and these three gases were present, because this reaction has such a small equilibrium constant, there would be very little NO present. It would be very little because it would react and form N2O2, NO2. Yeah. Oh, forgot this one down here. So the equilibrium constant says nothing about how fast a reaction gets to equilibrium. That's kinetics. That's chapter 15. So you can have an equilibrium that may take 3 years to form or longer. I mean, there are some processes that are just really, really slow. So what we're talking about here says nothing about how fast you get to equilibrium. We're just looking at, once you get there, what are the relative concentrations? So, summary of the significance of the value of the equilibrium constant. So K being very small, the reverse reaction is favored, the forward reaction does not go very far. And you can remember these by just thinking about the definition of the equilibrium constant. It's the product concentrations over the reactant concentrations. So what's going to make that a small number? Well, if the bottom is big and the top is small, right? So that means little product, a lot of reactant. When the equilibrium constant is around 1, and that's, like 0.1 to 10 would be considered around 1 compared to 10 to the minus 31, that means that neither direction is favored and the reaction goes about halfway. And if K is really large, the forward reaction is favored. It essentially goes to completion. The reverse reaction occurs very little. So in Chem 1A, we talk about reactions as if they all go to completion. And now we have to acknowledge that there are actually relatively few reactions that go to completion. A lot of them are equilibria. And the equilibrium constant may be quite high, so you don't notice that some of it didn't react. But it's very common for there to be small amounts of reactants left. Now, if you're talking about a non-reversible reaction, then that's something else. Okay, here we have a reaction of A going to B. A is the red circles and B is the black circles. And this is shown at 3 different temperatures. So this is temperature 1, temperature 2, and temperature 3. And it's asking at which of those temperatures is the equilibrium constant the largest? C. Because what makes the equilibrium constant large? A large amount of product. And so this one has more product relative, more product relative to the reactants than the other two. So we saw that rate constants depended on temperature, and equilibrium constants are also dependent on temperature. Here's another conceptual question. The equilibrium constant for this reaction A to B is 10. A reaction mixture initially contains A equals 1.1 molar and B equals 0. Which statement is true at equilibrium? Well, if we're doing the equilibrium constant expression for this, we don't have any coefficients here, so we don't have exponents, right? So the equilibrium constant is equal to the concentration of B divided by the concentration of A. And we're told that that's 10. So are we going to have more product or more reactant? More product. We're going to have 10 times more product than reactant, right? So which is the answer? B? In A, we've got a large amount of reactant and very little product. Here we have little reactant left and a large amount of product, and if you actually do the math, 1 divided by 0.1 is 10. And then C, the reaction mixture contains equal concentrations of A and B. Well, that's not true. If we wanted equal concentrations of A and B, and this was our reaction, what would the equilibrium constant have to be? It'd have to be 1.
I don't understand how saying there's more products than we have.
So this is the ratio of the concentration of the product to the concentration of the reactant at equilibrium. And so in order for this value to be equal to 10, B has to be 10 times larger than A. So if I put the numbers in, here I've got A being 0.1, so that's 0.1 down there, and B is 1.0 up here. And when I do the math, I get 10. Got it? Okay. Anybody else? Okay, so now we're getting to Spencer's question. So what if we do something to the chemical equation? The equilibrium constant has to change also. So this is a little bit like when we talked about Hess's law, and we take the equations and add them together, and if you reverse the reaction, you change the sign, and if you multiply by 2, you multiply by 2. So this is that same type of thinking, but the rules are a little different. So if you reverse the chemical equation, you invert the equilibrium constant. You don't make it negative, you upside down it. And so we can kind of prove that to ourselves using this simple reaction here. A plus 2B goes to 3C. And here's the reverse. 3C goes to A plus 2B. And so we can express like this. So C would be to what power? 3. And then we're going to have A and B squared down here. Right? And then if we look at this one over here, products over reactants, A and B squared over C cubed. So the difference between these two expressions is they are reciprocals. They're inverted, right? So if you want to reverse the equation, you invert the equilibrium constant. What if you multiply the coefficients by a factor? Then you have to raise the equilibrium constants to the same factor. So here we've got the reactions going in the same direction for both of these. Whoops. So here we have C cubed over A and B squared. And over here in the numerator, I've got the concentration of C, but now the coefficient is 3 times N. So the exponent is 3 times N. And then I've got A to the N and B to the 2N. Sometimes, like to make a mechanism come out or something, we need to multiply all the coefficients. by 2 or something. So if you multiply the coefficients by 2, you multiply all the exponents by 2 as well.
A few seconds ago, you said it's the same as multiplying the equilibrium constant by that number?
It's raising the equilibrium constant to the same factor. So K prime here is equal to K to the n power. Yeah. If you add equations to get an overall equation, you multiply the equilibrium constants. It's a little bit like the logarithm stuff, right? If you're adding, if you're multiplying, you add, etc. So let's see how this works. Let's add these two equations together and write the equilibrium constant and see how that works out. So I'm going to end up with A plus 2B is in equilibrium with 2B plus 3C. And then I realize, oh, that was dumb. I should have canceled those out. A is in equilibrium with 3C. So the equilibrium constant for that reaction would be C cubed over A. Yep. So let's see what happens if we take K1 times K2. So K1 times K2. That's going to be B squared over A times C cubed over B squared. And the B squareds cancel out, and I get C cubed over A. Hmm?
Can you cancel out the P's without writing that aloud, or is this just?
Well, what you'll do, this is showing you that it works. If you were actually doing this and you had numbers here, you'd add them together and you'd say, oh, well, if I'm adding these, I multiply these. This times this, and you get the number. Yeah, you don't actually have to do this all the time. But I think you'll agree here, this math is a little nicer than the math in chapter 15. Yeah, so much. It's like, whew. Well, I did manage to scare some people away. So, I got everybody who's still attending into the class. So I'm feeling pretty good about that. Okay, so let's test our skills here. The reaction A to 2B has an equilibrium constant of 0.01. What's the equilibrium constant for the reaction B going to 1/2 A? What we need to do is identify how is this second equation different than the first one. What's the most obvious thing? It's reversed, right? Here B is the reactant and there B was a product. So when I reverse the reaction, what do I do to the exponent? I'm due to the coefficient. No. What do I do to K? I invert it. So we're going to have 1 over 0.010. But what else is different?
It's divided by 2.
Yeah, we divided the reaction by 2, or we multiplied it by 1/2. Right? If we multiply it by 1/2, then we raise the K to the 1/2 power.
So it's
10. Because this is 1 over 100th, so that's 100 to the 1/2 power, and that's 10. Okay? I feel like absorption is happening. Your brains are at dynamic equilibrium. It looks like nothing's happening, but I'm pretty sure there's some churning going on inside.
Well, why are you putting that number in the denominator, not the numerator?
Because from this equation to this equation, we reversed the reactants and products. So then you invert K.
Okay.
Yeah. So I reverse the reaction from here to here. I switch the reactants and products. So then I invert K, 1 over it. And then I multiplied the coefficients by 1/2, so I raise K to the 1/2 power. Consider the following chemical equation and equilibrium constant at 25 degrees Celsius. There it is, 2.2 times 10 to the 6. Calculate the equilibrium constant for the following reaction at 25 degrees Celsius. Now, we're not using the 25, but equilibrium constants change with temperature, and so it's just specifying that it's the same. So, how are these two equations different? Well, for one thing, they're reversed. So let's actually, this was a little more complicated than A and B. So I'm going to take this one and write it reversed. So that's going to give me CO2 plus CF4 in equilibrium with 2COF2. And if I do that, I'm going to take the equilibrium constant and invert it. So I'm going to raise it to the -1 power to the -1. So that's 1 over K. And so this is closer to that, but this has all its coefficients multiplied by 2. So I multiply by 2. If I multiply by 2, then I multiply this exponent by 2 as well. And so this becomes, let's see if I can erase that, -2. If you don't like the negative exponents, you can also say, well, it's 1 over 2.2 times 10 to the 6. Whoops. And then I'm going to square the whole thing.
It's 2.066 times 10 to the
15. So just, trying to pay attention to sig figs, we'll probably call that 2.1 times 10 to the -13. Any questions?
Where did you get the -2 exponent?
Well, I had a -1 because I reversed the reaction. Or you can write it as 1 over 2.2 times 10 to the 6. And then I had to multiply by 2.
The equilibrium constant is always unitless.
Yes. Yep. Any other questions? (2.1 times 10 to the -13). Predict the equilibrium constant for the first reaction given the equilibrium constants for the second and third reactions. So these are awfully close together. It's kind of hard to look at them. So I'm going to sort of highlight that one. That's what we're trying to do, and this is the information we're given. So what we need to ask ourselves is, how can I combine these two equations to get the highlighted one? There is adding involved,
Invert the first.
and I have to invert one.
Invert the first.
Yeah, because this has H2 as a reactant. There's no H2 as a product. this one has H2 as a product. And I need H2O as a product. This has H2O as a reactant. So I'm going to write this one backwards. CO2 plus H2, making CO plus H2O. And then what do I do to the rate constant? Invert it. So I think people prefer to look at it actually 1 over, like that. So this is 1 over K2. And then let's put the other one in here. Plus 2H2. And let's see, is that going to be good enough? When I add those together, the COs go away, and I'm going to get 3 H2s here. CO2 plus 3 H2. And I've got CH3OH and H2O. So the second equation, did I do anything to the rate constant? No, it's just the same. I didn't do anything to the equation. I don't do anything to the rate constant. So that's still 1.4 times 10 to the 7th. And so down here, what I'm going to do is I'm going to take these two things and I'm going to multiply them. So I have 1 over K2 times K3, which is K3 over K2, right? 1.4 times 10 to the 7th divided by 1.0 times 10 to the 5. $140.
Instead of adding, this is what we multiply.
Right. Yes.
So, see, like for, you know, for Hess's law, if it's multiply by 2, or like, say you wanted to get the coefficients the same, you had to multiply all of them by 2, and then you had to do the heat, you have to multiply that by 2. Also, it's the same concept, right?
It's the same concept, but if we're multiplying here, we're raising to a power. It's like you're taking the math operation up a level, like there's adding, and adding goes up to multiplication, and multiplication goes up to raising to a power.
So you don't know, sometimes it'll have a fraction as a coefficient,
Mm-hmm.
so you would raise it to it.
Yeah, you could have a fraction as an exponent. Mm-hmm. Any other questions? The adding up the equations part is exactly the same. But how we manipulate the rate constant is different than how we manipulated the delta E's or delta H's because of how they're defined. 140.